Is it cool? You look at my.
Let me set up for the lecture and then I'll come over. Yeah. Hey, I'm gonna need to talk to someone else first. Let me set up a bit first. I'll talk to him and then I'll come talk to you. Yeah.
Support. It's not. Yeah. This is what I was worried about. Even though you it's really hard. Oh, I think because of geometry, it's really hard to see. Yeah, that's why I thought either a couple ways I know. Put that as a support here. And so what's going to happen if it's supported? The action force that naturally. So even though you don't apply it as a force here, there is going to be a way. Oh, that seems pretty. This is pretty. Yeah. Yeah, it's just whether you want to. Okay. Yeah. Okay. Maybe. And then it's so the only difference is the fewest friction is the makes it kind of shear a little, but even then. Yeah. Right. So the only. It would cause like shearing. I wouldn't do yeah, awesome. Okay, thank you. Great. And then so far I got so I know there were problems and then variations. Yep. Here. So okay. Okay. It's like the bind just used to have. Yeah. Also be KA plus IB. It'd be KA plus KH. Okay, for each part it's over here. I'm gonna go KA. Yes. Oh. Yes. Yeah. That's why I said on the Discord just treat them as and then they'll overlap.
Exactly.
So I had to write the first thing.
Yeah, so treat them all. Yeah, that's why I said don't worry about the line. It's gonna come out just naturally.
As far as what I am the force experience.
They would, well, they're experiencing the same force, but it's zero. Because we're not, remember the boundary conditions are just external. And so internally, yes, they're going to be experiencing forces with this pressure. They're internal. And for everything here, it's all external forces.
So this would all be just 0, 0.
Exactly. Yes, we F1 is 0, F2 is 0, F3 is 0, F4 is. I'm sorry, I'm not. Okay.
Yeah, it's cold. All right, it's 5:30. Let's go and get started. Let's find where we are. Here we are. Okay, so good evening, everyone. How's everyone doing today? Okay. Yeah, it's cold. Yeah, it's nice actually. When I was little, I used to hate cold weather, but now that I'm older and grumpier, I guess I like cold weather better now. It's easy. It's a lot easier to sleep at night when it's cold. That's for sure. Okay. So we actually don't have that much more to cover today in terms of the beam, equation. So I have just kind of one more example to do. So what I did today, and you may have noticed this already on Canvas, I put up information on the final project, and so that's true too. Cheaper bills. That's always a good thing. And so what I'm going to do today, I'm going to spend the first half hour today talking about the final project. I know we just got done with the midterm project, and I'm just about maybe, I'd say about 2/3 done grading the midterm project. I did the 2/3 yesterday. I knew I wouldn't have any time today just because we've had a meeting today and lots of other fires to put out today. So I haven't been able to work on it today. But I should finish it up by tomorrow, and so you should know what your midterm project score is tomorrow. But I thought, today, I don't think we're gonna have a full lectures worth of content in terms of beam equations. So I thought I'd introduce the final project today, just so you know what it is and kind of what to look out for, because I do want you to submit a proposal for that in a couple of weeks, and so I want to make you aware of that, and then we can go. Okay, so that's the plan for today is. Talk about the final project and then finish up the beam equation notes. We still might end a little bit early, but we'll see. Okay. All right. So that's all my announcements. And so are there any questions I can answer before we get started for today? Okay. All right. So let me go ahead and let me switch to my podium screen here. Okay. All right. And so I'm on Canvas right now. And so if you go to the assignment page, you'll see that I've posted two things for the final project. And so I posted the final project itself, which is this is the assignment where you're going to submit the final reports. But then I also have an assignment here for a proposal, and we'll talk about that in a second. Okay. All right. So let's do the final project. Let's talk about the specifications. Okay. All right. So the idea with the final project is that it's basically just going to be a repeat of your midterm project mostly, except with your own geometry. Right? December 24th. No, it's a little bit too close. I want to have Christmas with my family, and so I want to have it due before then, so I can finish grading. Yeah. Okay, and so the idea with the final project is that just like the midterm project, you're going to be doing kind of what I consider a full finite element analysis, and so you're going to be taking the geometry, you're going to be meshing it, find boundary conditions, running simulations, and justifying every step of the process. Okay? So hopefully you kind of got that theme from the midterm project where, finite elements, a lot of it has to do with, how you justify your decision making. And so your decisions for the mesh, your decisions for the boundary conditions, all that stuff. So you're going to do all that same as the midterm project. But for the final project, I'm going to let you choose your subject. Okay. And so for the midterm project, I gave you, 3 choices for the geometry, but I know that, a lot of you are in senior design or, or you're working on other projects. And so, I've always wanted one of my visions for this class was always for it to be useful to you, not only in, what you're learning, of course, what you're learning is useful, but I know a lot of you are working on other stuff as well. And so I've always wanted this class to be useful for those things too. Okay. And so, this final project here is kind of your chance to perform that analysis to kind of have a supplement, maybe what you're working on in senior design, or maybe what you're working on for formula or for rover, and so, this has always been such a good, I think, opportunity for that. And, I want to continue that tradition. Okay. And so, I think the first step of this final project is to choose, what you want to do finite element analysis on. Right. And, that's part of the reason why I have the proposal too. And so, before you start working, before you start meshing and simulating, I want to at least kind of know what you're planning on working on and kind of sign off on it before you kind of get off to it. Okay. Because what can happen, as is always the case when you can kind of choose your own subject, is that scoping it becomes difficult because, I think for a lot of you, this is your first time, using finite elements. It's easy to, either overestimate or underestimate kind of what you can do with finite elements and still have it be useful. And so the reason I have a proposal is so that, you can let me know what you're working on. You can show me the CAD model and I can tell you, I think this is good. I think this is not good. Maybe you can consider this or not. Okay. And actually, the problem that I generally have with this class is that it's not that people choose projects that are too easy. It's actually that people choose projects that are too hard. And so, what you'll see for a lot of you is that you're going to submit your proposal and you're saying, like, here's my CAD model. I want to do finite elements on this. And it's going to be awesome. I said, that's going to be awesome, but you're probably going to need 3 months to do this. And so, we don't have 3 months. And so we just have you basically just have a month to work on this. And so for a lot of you, I'm going to say, let's pare it back a little bit. Let's, let me consider a simplified version of this. And so, that's kind of the reason why I have that. Okay. But really, it's up to you. And so you can choose what you want to work on in this project. The only requirement that I have is that you kind of supply your own CAD model. And so I'm not going to be producing any CADs for any of you. And so you can either, if you have it already, just based on the project that you're working on, that's great. There's a lot of online repositories that you can look at too. And so, a lot of people in the past have used GrabCAD and they've gotten a CAD model from there and used that for their final project. I think that's a great option. And so, be creative. And so, at this point, we're 11 weeks into the course. And so I think, there's probably a lot of you, are probably saying, I want to try finite elements on this. Well, this is your chance to do that. Okay. All right. So let's talk about the specific requirements. So a lot of this is going to overlap almost directly with the midterm project, which was kind of my goal. So that, the midterm project is kind of your trial run. And then the final project, this is kind of the real deal stuff. Okay. And so first of all is the objective. And so, so far from what I've read from your midterm project reports, most people are doing a pretty good job with this. But remember, when you do a finite element analysis, there has to be some kind of objective. There has to be some kind of information that you're looking to obtain. And, for the final project specifically, maybe that information is going to inform your design. Okay. And so maybe you're working on, a specific component of a design and you want to see if you can save cost, right? And so you're seeing, can we save some material here? And so what I'm going to do is I'm going to run a finite element simulation. I'm going to compute the deformations. I'm going to compute the stresses. I'm going to see if those things are still within factor of safety and then try to, maybe shave off some material in order to save on some cost. Okay. So that would be kind of a good example of, of an objective that you can use for this final project. Okay. And so it's more than just saying that, I'm curious what the total deformation is. I'm curious what the equivalent stress is. Okay. It's more, what are you going to do with that information? And so, why is the stress relevant? Why are you computing that? Are you curious to see that, is this enough to hold this load? Or are you curious to see, how much load can it handle? Okay. And so remember, it's kind of about how you use that information and how that's going to form your objective. Okay. All right. Second requirement is the background and significance. And so this is going to be a lot more exciting this time because, you're all kind of bringing your own subjects to the table. And so the background and significance for each one is going to be different. Okay. And so among the 30 projects that I've graded so far, I've read so many thrilling life stories about the wall bracket. So the wall bracket is the protagonist of a lot of different stories, which is great. You know, the wall bracket is doing a lot of work, but you know, I think it's going to be more exciting to see what your subject is going to be and why it's significant. Okay. And so, you know, a good example for this is that if you're working on, you know, if you're going to be doing the final project on your senior design, you know, tell me a bit about your senior design project. And so tell me, you know, what are you designing for? What are the goals of the design and stuff like that. Okay. I did see yours, Roman. I did get a good laugh out of it. I think I should, maybe I'll pay you to make that plaque for me someday. All right. The next one. So this is going to be a new one. And so the next one is what I call a validation calculation. Okay. And so after Thanksgiving, we're going to learn about, or actually maybe before Thanksgiving, you know, we'll learn about this important aspect of finite elements called verification and validation. Okay. And so what that's all about is, you know, finding different ways to check your work in finite elements. Okay? Because when you work in simulations, you know, what can happen a lot is that you end up kind of trusting your simulations a little bit too much. Okay? But you know, but I think, you know, we all know at this point too, is that if you make kind of one small mistake with the boundary conditions, or maybe your mesh isn't good, then the results that you get from your simulation may not be accurate or may not be reliable. Okay? And so it's always a good idea to check your work in some way. And we'll talk about this a lot more in detail. And so, you know, you don't have to worry about this too much just yet. But what you can kind of expect is that in addition to your finite element simulation, I want you to do at least one hand calculation, or maybe you check your simulation results against some data that you have. And so if you have some kind of measurements that you've taken on this particular part. And so I basically want you to check your finite element results in some way. Okay. And so, you know, I leave that kind of purposely vague because, you know, what you do for validation and what you do to check your work is going to be different for everyone. And so it's going to depend very heavily on what your subject is and what you have available to you. But the point is, you know, I want you to check your work in some way. And I want you to check your work in a way that doesn't involve ANSYS at all. Okay. Because that's always something good to do. Question. So a lot of these seem very similar to the project we signed a little while ago. Yeah, no, that's the point. And so, you know, I wanted the midterm project to kind of be like a trial run for this stuff, and then you're going to be doing it kind of again for the final project, but only on just your own subject. Nice, that's good. Question. So do you get extra credit if you do a complex calculation? No, it just has to be. It just has to make sense. And are you allowed to use MATLAB? Yes, you are allowed to use MATLAB for that. Okay, question. The calculations you said to do by hand. Yeah. And so maybe I should revise this. So it's anything other than ANSYS that you can use to simulate. Yeah. Yeah, I think maybe I'll revise this and I'll put it up. So it's just anything other than ANSYS. Yeah. Okay, finite element methodology. So this should be very familiar to you. And so just like the midterm project, you know, you're going to be making decisions on the material properties, on the meshing, on the boundary conditions. And so I want you to describe all of that in excruciating detail. And I want you to, you know, justify why you're doing a lot of those decisions. Okay? And so, you know, you should pick a material that, you know, if you're doing this for senior design, you know, tell me the material that you're using and, you know, and put the properties in there and tell me why you're using that material. Okay? For your meshing, you know, where are you putting most of your elements? What element order are you using? What shape are you using? Okay? And so, and tell me how many elements that you ended up with. And same thing for the shape as well. Okay. Boundary conditions, you know, they should make sense, and so, you know, they should make sense relative to you know, what your subject is. Okay. And this is an important one too. So one thing I noticed a lot in the midterm project so far is that, you know, not only do I want you to justify, you know, where the loads are and what kind of loads that you're putting on there, but I want you to justify the magnitudes of the loads too, because I saw a lot of times where, you know, in the midterm project reports, I saw someone said, you know, I'm going to put a 300-pound load on this wall bracket. And I'm like, okay, that's great, but what does that 300 pounds represent? And so you want to make sure that, you know, when you're applying your boundary conditions and you're choosing the directions, the locations, and the magnitude, all of those kind of have proper justifications. Okay. And so, you know, it should be something that kind of realistically should happen to your, you know, to your design. Okay. And one thing that I'm adding here is that, you know, in addition to justifying all those things, I want everyone to do a mesh convergence test on your final project as well. So I know some people did that already on the midterm project, which is great. But for the final project, it's going to be a requirement. Okay. All right, so the next section is your ANSYS results. And so this is pretty straightforward. And so I think, you know, I think everyone here knows how to display their ANSYS results by now. And just like the midterm project, I want you to come up with 3 different configurations for your subject. Okay. Just like the midterm project, you know, at least 2 of those should be unique. I want at least 2 unique boundary condition setups, and so you should change up the loading. Maybe you change up the supports. Okay, and then for the third one, you can just change the material, just like the midterm project. Okay? But that's kind of more or less exactly as it is, you know, for the midterm project. And so the next section is I want you to compare your ANSYS results with your validation calculation. Okay. And so whether you're using MATLAB, whether you're using hand calculation, or maybe you're using some kind of experimental measurement. And so I want you to kind of have a look at how your ANSYS results compare to your validation. Okay. And I'll say that, you know, it's unless you have a very kind of specific case, I would say that for most people, you're probably not going to have a good matching. And so just because you know, we're kind of limited in terms of what we can do for validation, but you know, I at least want you to think about it, and I at least want you to kind of get into that mode of thinking, because that's something that's important for professional FEA. Yeah. I won't publicly endorse that statement, but you know, if you do find one, I won't complain too much. And then finally, the conclusion. Okay, and so conclusion. There's going to be some discussion questions too, so I'll have that on the report template, just like on the midterm report, and so that's going to be exactly the same. Okay, and so those are the main deliverables, and so those are kind of everything you know, that I'm going to expect. And so you can see, you know, a lot of it overlaps with the midterm project, you know, which was kind of the point, except now you're going to be applying that same process to a subject of your choice. All right, any questions on this? Yeah.
I saw that we can.
Yes.
So can we make that our primary study?
Yeah. Yep. Yep. And so, yeah, I did kind of gloss over at the beginning, but you know, FEA, you can do a lot more than just structures. And so if you have a thermal situation that you want to study, we're not going to go over the heat transfer stuff too much in the class. I do have some handouts that I can give to you, and I think we'll probably spend a day on it. But if you want to do thermal for your final project, absolutely you can do that. And probably what's going to happen is that I'll probably be working with the thermal people just to kind of help you set it up a bit. But yeah, absolutely. All right, so let's talk deliverables. And so there are 2 kind of main deliverables for this project. And so the first one that you're going to do is just a proposal. And so the proposal is nothing too big. I don't want you to spend too much time on it. It's just a way for me to just be aware of what your plan is, and for me to kind of give you feedback in terms of, you know, what's feasible to do in the time that we have. Okay. And so here I say that, you know, you could write a 1-page proposal, but it doesn't have to be a page. It can be less than that. The main thing that I want to see is, you know, first of all, you know, tell me what you plan on working on. If you have a CAD model already, you know, show me a screenshot of a CAD and say, you know, this is the model. I'm going to import this into ANSYS. And, you know, I'll be able to tell you, you know, what's good or what's not. Okay. And 3 here, you know, I said that you should have an idea of what your validation calculation will be. You know, maybe you don't have a concrete idea of that yet, but at the very least, you know, I want you to have, you know, your CAD model. If you have it already. If you don't have a CAD model, just kind of describe to me what you're thinking and kind of where you're going to get the CAD model, and just a brief description of kind of what you're going to analyze and how you're going to load it. Okay. And so, you know, I don't want you to spend a lot of time on it, but I do want to see this, you know, before you kind of get started. So this is going to be due in about 2 weeks. And so I want to give you a bit of time after the midterm exam. And so the midterm exam, remember, is on the 17th. And so I'm going to make this due on the 20th, which is the Sunday afterwards. Okay? I am going to grade the proposal. I'm only going to grade it for completeness. And so it's worth about 10% of the overall points on the final project. And so as long as you turn in the proposal, you turn in by the deadline, then you get an automatic 10% on the final project, which is good. Okay. All right. And the other thing that you're going to turn in is the final report. And so, you know, we just talked about the final report. So the final report is going to have all the required sections that we talked about up there. Okay. And the due date for the final report, so this is the ultimate due date for everything, is going to be Monday, December 19th. And so that's the Monday after finals week. And so I know you guys have a lot of stuff going on during finals week, so I never want to make it due then. But I do want to give myself enough time to grade it before Christmas, so I can see my family, spend time with them. And so, the 19th, that's kind of the latest that I can have it due, while still being able to grade it before Christmas, and that but also giving you guys as much time as you need to work on it. But with that said, please don't be afraid to turn in early. And so if you finish it early, and you can submit it during finals week, I'm actually, for this semester in particular, I'm going to be pretty bored because I don't have any final exams in my classes. So if you can let me get a head start on grading, I would greatly appreciate it. But but the deadline is not going to be until the 19th. Okay. Any questions on the deliverables? Questions. So in our senior, yeah, I think that's cool. If I want to do 3 different simple models, maybe we can talk a bit more offline about it. But I think that sounds interesting. Yeah. Okay. All right. So the last thing I want to talk about is teams. And so, I do strongly prefer that everyone do this project individually. Just because it's like the midterm project, I think, a finite element simulation is kind of enough work just for one person. But I do know that, a lot of you are in this class, together with either people in your senior design group or maybe people in your, in your project group. And so, I am open to the idea of teams. But I want you to come talk to me first, before I say that I want to work with so and so, and how should we approach the project? Because of course, if you're going to be working together, I am going to be expecting more, and so I want to talk to you first so that so that we're both clear on kind of the expectations in terms of what you're going to do. Okay. And so with that said, the largest group that I'll accommodate is just groups of 2. And so if you do want to work with someone, you can come talk to me, and then we can probably work something out. But unless it is something that's going to be complex enough or enough work, I might ask you guys to do individual work, but maybe different aspects of the same project. So I think that's usually a bit more appropriate. Okay. But sometimes depending on the subject, depending on the project, maybe it's enough work for 2. So I leave it open, but if you do want to work with someone, just talk. All right, and so final remarks. It's just like the midterm project, just like you've probably already experienced. Producing FEA it's a lot of work, not only in ANSYS, but there's a lot of writing and documentation that you have to do. So please don't hesitate to reach out if you have questions about anything. My job here is to make sure you guys are as successful as possible, and so I enjoy doing that part of my job. And so please reach out to me. I'm always happy to talk. Especially with this project, I always have. I know it's a lot of work for you guys, but from my perspective, this is probably one of the most fun things that I do. Just seeing what you guys can come up with and seeing all your finite element simulations. It really is kind of one of the highlights of the semester for me. So I'm always happy to chat with you guys about this. So don't be afraid to reach out. Okay. And kind of the other goal that I have with this project is that I want you guys to have something concrete that you can have in your portfolio that you can submit to employers. And so, I know a big reason a lot of people are in this class is because ANSYS is a very desirable job skill. So a lot of companies are looking for ANSYS, and they're looking to hire people that can do ANSYS. And so I want you to have something that you can submit and say, this is a report. This is something that I produced that shows that I know ANSYS, right? It's one thing to have kind of a one-liner in your resume to say like, part of your skills that you can do ANSYS. And maybe you can say that you took a class on it, but this is something concrete that your employer can see that not only can the student they know how to do ANSYS, but they know how to actually organize their thoughts on ANSYS. They know how to actually justify. They know a lot of the theory behind finite elements, and so we can hire this person with a confidence that they can step in and do ANSYS on day 1. Okay, and so that's kind of the other motivation with this project. And so by the end of it, I know it's a lot of work, but by the end of it, you're going to have a report that you can say, hey, employer, this is something that I can give you that shows I can do ANSYS. And so, that's I want you to have something like that that you can take away from this class that that you can use. And I've had a lot of people over the years. This is the fifth time that I'm teaching this class, and so this is the class that I probably taught the most here at Cal State Fullerton. And every year, people come back to me and say, I showed them what I did for my final project, and I got a job from it. I'm like, that makes me so happy. That's awesome. And so I want to kind of continue that. And so this final project is kind of that that way of kind of showing people that you can do ANSYS in the professional setting. All right, any final questions on this? Are you allowed to resubmit the final project? What do you mean by that? You're only submitting the final project once. Oh, before, yeah. Oh, yeah. If you submit it before the due date and you want to make some changes, you can submit another copy. That's totally fine. Yeah. Yeah, as long as it's before the December 9th deadline or December 19th deadline, then you can submit it as many times as you want. Okay, all right. So all that information is on Canvas, and so feel free to take a look at your heart's content. Okay, and so let's go ahead and come back to kind of where we were on Tuesday. Okay. All right, and so just to kind of save myself some time, I'm going to kind of scroll up here. Because where we left off on Tuesday was talking about this idea of distributed loading, okay? And so the idea with distributed loading is that a lot of times when you're doing finite elements, the loads that you're applying onto a subject is distributed over certain area, over a certain line in this case, okay? But that's a little bit inconsistent with what we've been doing with the direct stiffness method, where all of our loads are applied at the nodes, okay? And so we kind of have a disconnect. And so, on the one hand, we like to apply our boundary conditions distributed over an area, but in order to actually do computations on it, we have to convert those into nodal loads so that, we can actually do that, okay? And so what we're doing now is we're basically looking at a way to do this conversion. Okay? So how do we go from a distributed load, which is kind of this continuous function that you'll see, and how do we transform that into discrete nodal points and to make sure that they're equivalent? Okay. And so to do this, we utilize this concept called work equivalence. Okay. And so basically the idea behind that is no matter what form the load is, whether it's in a distributed form or whether it's in a nodal form, it's going to perform some work on the structure. Okay. And so it's going to cause it to deform. And then if we multiply the force of the loading multiplied by the deformation, that's going to give us the work. Okay. And what we said is that no matter what form the loading is in, it should perform the same amount of work because it should be the same loading. Okay. And so what we have here is kind of this equivalent statements right here. Right. And so what we say is that if we take the integral of the distributed loading, so this P here is distributed load, right? Where for this part, we're going to assume the distributed loading has units of newtons per meter. Okay. So it's a line load, so it's a load that's distributed over a line. We multiply by d of x, where this d of x here is the deformation of the beam. Right, if we integrate that with respect to dx, which is the dimension along the beam, this is going to be equal to all of our nodal loads. Okay, and so F1y, F2y, M1, and M2. Okay, all these are our nodal loads. So that's what we're solving for, and they're going to be multiplied by the nodal deformations. And so in orange here, these are the nodal deformations. and those will kind of leave as they are. Okay. So this is the equation that we're working with here. And we kind of left it at this, but this is kind of the one equation that we're going to be working with all throughout. All right. And so I'm going to leave the right side of this equation alone because that's ultimately what we're going to be solving for. And so basically we're going to the way we're going to use this is we're going to evaluate the left-hand side and then set it equal to the right-hand side to solve their values. Okay. So we're going to be working mostly on the left-hand side. Okay. And so we have two main functions here on the left-hand side. So we have P of X. And so P of X, let's remember our distributed loading. And so most of the time, this is either going to be given to you or it's something that you specify, okay? And so, we can assume that this is known. Maybe known is a better word for that. Okay. Right, so we're not going to worry about P of X. Okay, because we know it because that's whatever our loading is. Okay? Kind of the mystery person here is actually D of X. Okay? And so let's read the description for D of X again. So the D of X here is the beam deformation as a function of X. Right? So that may seem benign, right? And so that may seem kind of, yeah, that makes sense. But we haven't actually come up with such a function, right? And so the key to this whole operation here is, how do we form this D of X here? Because it's something that's, that it seems like we haven't looked at it, but then there's also ways that we could look at it as well. Okay, so actually, let me come down here. And let's talk more about this beam deformation function. Okay. Draw beam. So here's our beam. We'll assume that the X direction is this way. Right, so the X direction kind of goes along the beam. And so what we want to discover or what we want to compute is how the deformation changes as a function of X down the length of the beam. Okay? Okay. The only problem with this is that we haven't come up with such a function yet. And so, if we think about all the direct stiffness problems that we've done, we're only able to solve for the deformation at the nodal points in the mesh. Okay? We don't get a continuous function. We only get the nodal deformations. And so we kind of have to reconcile these two ideas here, okay? Because let's say that we split this beam up just in two, okay? And so with the direct stiffness method, we'll be able to compute what the nodal deformations are at node 1, node 2, and node 3, okay? Those distinct locations. But when we say that we want d of x, we want to know how the deformation varies in the space between the nodes. Okay? So that's going to be our goal here. All right. And so to get that function, we're going to need to bring in a little bit of beam theory. So let's go back and let's go ahead and look at our governing equation for the beam. So for a simply supported beam like this, we have E times I times the fourth order derivative of the transverse deformation with respect to X, okay? And this is all equal to 0. So what we can kind of postulate, and so based on this governing equation right here, obviously it's a differential equation. And so based on this differential equation and based on the nodal solutions, we can come up with a function that kind of satisfies both at the same time. Okay. Sorry, not uy of x, dy of x. I keep changing that. And so for a typical beam right here, I'm just going to use nodes 1 and 2 just because it's simple. Okay. And so for a beam member, we have 4 nodal deformations. So we have D1y, we have theta 1, and then D2y, and theta 2. Okay. All right. And so if we say that the length of this beam is L, and so on the left side of the beam, we have x is equal to 0. And on the right side of the beam, we have x is equal to L. Okay. What we're saying by this statement here is that dy of x, which is the function that we need to plug into our work equivalence, it must satisfy these conditions. First of all, the dy of x, it should solve the equation above. We have dy of 0 is equal to d1y. Okay. Okay. Remember, theta 1, theta 2 are the rotations of the beam at those locations. And so one way that we can express rotation is we can take the derivative of the deformation with respect to x. Okay. And so we take the derivative of it with respect to x, said x is equal to 0, and that's equal to theta 1. Okay. And we have the same conditions on the other side. So dy of L is equal to d2y, and dy dx at x is equal to L is equal to theta 2. Okay. All right. And so what we can do from here is, we can, these 4 conditions here, we can think of them almost like boundary conditions, okay? And so we can use this to solve the differential equation up there, because what we can do is we can divide both sides by EI. And so if we divide both sides of the differential equation by that, the EI is going to cancel out. And so, we're no longer going to have that. And since we have a fourth order derivative equal to 0, what we can do is we can just simply integrate this thing 4 times. Right? Right. And so I'll spare you the pain of the math. And so, whenever you have a derivative equal to 0 and you just integrate it repeatedly, what you're going to get is a polynomial. Right? And so if we integrate it 4 times, we get the following general solution. And so we get dy of x is equal to C0 plus C1x plus C2x squared plus C3x cubed. Okay. And so we get a cubic function basically. Okay. And so what's nice about this cubic function is if you count the number of unknown coefficients, and so these are all the C values. So we have C0, C1, C2, and C3. Okay. If you count those up, we get 4, right? So we get 4 unknown coefficients. And what else do we have 4 of? We have 4 fingers, but we also have 4 boundary conditions. Okay. And so we can use those 4 boundary conditions to solve for those unknowns. Okay. And it's a very painful process. And so I'm not gonna subject you guys to that. But if you are really into algebra and, maybe you're out of Sudoku puzzles for today or something, but then you want to verify this. But basically what you're going to plug in is all of these boundary conditions and solve for C0, C1, C2, and C3. Okay. And so if you get all that, you get the following result. Okay. Eventually, after a lot of math. Let's get dy of x is equal to 2 over L cubed d1y minus d2y plus 1 over L squared theta 1 plus theta 2. Well, this is multiplied by x cubed plus minus 3 over L squared, okay, minus d2y minus 1 over L, 2 theta 1 plus theta 2 squared plus theta 1x plus d1y. So it's a doozy. And so, it's a lot of terms there, mostly just because, we don't have concrete expressions for that. Okay. All right, any questions on this? Okay. All right, so now that we have dy of x here, what we can do is we can plug this into our work equivalence equation above. Okay. And when we combine that together with with the loading function, then we'll be able to compute the nodal loads. Okay. And so, I think the best way to kind of illustrate this is with an example. So I have a fairly lengthy example. So I think maybe it's going to take quite a while. And so you can see kind of all of it in action. Okay. But it's going to involve a lot of algebra, a lot of integrating, but but we can get through it. All right, any questions on this? Okay, all right, so let's jump into an example to kind of show you how all of this kind of fits together. Okay. So let's consider a situation where we have a beam that's subjected to a ramped loading. Okay. Here's our beam. So I have node 1 on the left, node 2 on the right. And then the load on here is going to start at 0. And it's going to ramp up just like that. Okay. And so the function for this loading is going to be 5,000 times x, and the units are newtons per meter. Okay. All right, so you can see our loading function here is a linear function. So it starts out at 0, and then it ramps up as you get to higher values of x. Okay, so we have 5,000 x. All right, so in this problem, what we're going to compute is we want to compute the equivalent nodal loads at points 1 and 2. Okay. Right, so basically what we want to compute is we want to compute the values of F1y, F2y, M1, M2, okay, for this beam. And just for simplicity, just so we don't go crazy with algebra, we're going to assume the length of the beam is 1, okay, 1 meter. All right, and so we're going to use our formula for work equivalence together with our beam deformation function, which we have above, together with our distributed loading function. And we're going to evaluate all that. And then we're going to get our solution for F1y, F2y, M1, M2. Okay. So that's the setup for the problem. So any questions on this? Okay, so let's go ahead and do it. So we're going to use our formula for work equivalence. And so we have integral 0 to L, P of x, multiplied by dy of x, dx. This is equal to F1y, d1y, plus F2y, d2y, plus M1 theta 1, plus M2 theta 2. Okay. Remember, so what this formula is saying is that the work performed by the distributed loading P of x, that has to be equal to its equivalent, the work done by its equivalent nodal loads, okay? And so we know what P of x is. We know P of x is 5,000 times x, and then let's go ahead and let's plug in for that, and let's plug in our beam deformation function, okay? So let's go ahead and plug in. And we're going to plug in for this side of the equation. All right, so we have integral from 0 to L. P of x is 5,000 times x. Okay. And then dy of x is the following. So we have 2 over L cubed times d1y minus d2y plus 1 over L squared, theta 1 plus theta 2. That is multiplied by x cubed plus -3 over L squared, d1y minus d2y minus for L 2 theta 1 plus theta 2. That's multiplied by x squared plus theta 1x plus d1y dx. Okay. All right, so I've just done the left-hand side. So the right-hand side of the work equivalence, we're just going to leave it alone for now because we're going to use it as reference later. But we have a lot of work. We have enough work cut out for us here on the left-hand side. Okay. Okay. So let's go ahead and simplify this. And so I'm going to simplify it in kind of a strategic way, just to kind of minimize the amount of integration work that we have to do. Okay. So first thing I notice here is that we're integrating with respect to x, right? And so that means that we should keep the x terms as they are. So the only terms that have x here are this x that's kind of out in front. That x is going to get distributed all throughout this entire function here. We have this x cubed here. Okay, the x cubed has a ginormous coefficient, but that all that is relatively constant, and so we just have to worry about the x cubed. We have an x squared here, again multiplied by ginormous coefficient, but we can go ahead and leave it alone. We have a regular x by itself, and then we have d1y. Okay, so first thing I'm going to do is I'm going to distribute the x from p of x into the dy of x function. And so what you're going to see is that it's just going to increase all the x values by 1. And so instead of x cubed, it's going to be x to the 4th. Okay. Next thing I'm going to do is I'm going to take the 5,000 because that's just a constant. I'm going to extract it out from the integral. And then last thing I'll do, and I'm writing all this down because it's kind of a lot to do in one step. Last thing I'm going to do is I'm going to plug in L is equal to 1, okay, just to kind of save myself some writing. And so since L is in the denominator a lot for these terms, plugging in L is equal to 1 is going to save us a lot of time. All right, so let's do all those steps there. So first we have 5,000 because that's going to come out in front. Then we have integral. The integral is from 0 to L, and so we're going to have between 0 and 1. Okay. First term that we're going to have here is 2 over L cubed, and so since L is 1, so we're going to have 2. Okay, because 2 over 1 cubed is just 2. And so that's 2 going to multiply by d1y minus d2y. Plus 1 over L squared. So 1 over L squared. L is equal to 1. That's just going to be 1 over 1, which is 1. That's going to be then just theta 1 plus theta 2. Okay. We're going to close the parentheses here, and we're going to multiply that by not x cubed, but x to the 4th. Okay, remember we distributed that x throughout. So this x is going to be multiplied into here, multiply into here, here, and here. Okay. So that's the first term that we have. Next, we have a minus 3 over L squared. So that's just minus 3 times d1y minus d2y minus 1 over L, which is 1, 2 theta 1 plus theta 2. And so then we're going to multiply by our x term, but instead of x squared, the x is going to be multiplied, x squared is going to multiply by x. So this becomes x cubed. Okay. And we have the final two terms here, which are just, pretty straightforward. So we have theta 1x. And so instead of theta 1x, we have theta 1x squared. And we have d1y by itself. And so that's going to be d1yx. So hopefully this is making it look a little bit less intimidating. So I know we had a lot of terms in this expression here, but a lot of them are just constants. And so remember, when you have constants in an integration, they just carry right on through. So we can just kind of leave them alone. The only terms that we're concerning ourselves with are just the x terms, and these are the ones that we're actually going to integrate here. Okay. Ex. All right, any questions on this? Okay, all right, so let's go ahead and continue. So now that we've reached this step here, we've kind of done all the simplifying we can do for the integral itself. And so let's go ahead and integrate. All right, so we perform the integration. We can't forget the 5,000. Okay, we end up with the following. And so all of the constant terms I'm just going to bring straight down. We take integral of x to the 4th. That's going to be x to the 5th over 5. Then we have the coefficient in front of the x to the 4th. And so that's minus 3 d1y minus d2y minus quantity 2 theta 1 plus theta 2. We take integral of x cubed. We get x to the 4th divided by 4. Okay. Then we have theta 1 x squared. We integrate that. We get theta 1 x cubed over 3. Then we have d1y x. We integrate that. That's d1y times x squared over 2. Okay. And since we integrated this, we're evaluating it between 0 and 0. All right. And so hopefully you see why I kept certain terms together as they did, so that when we integrate it, it becomes simple. So all kind of the nastiness, remember, is from the constants, and so we just kind of carry those through. Okay? We're going to deal with those very soon, but for now, we just kind of leave it as it is. Okay. All right, so now that we've performed the integration, we can go ahead and apply the bounds. Okay? And so luckily for us, our bounds are very simple here. So they're just 0 to 1. And so when we plug in x is equal to 0, everything here is multiplied by an x term at some point. And so when we plug in x equal to 0, that's just going to make the whole thing 0. And so we only have to worry about plugging in x is equal to 1. And luckily, even though we have a lot of scary exponents here, 1 raised to 50 bajillion is still 1. And so, we can still plug in just 1 for all the x's here. Okay? All right, so when we plug in for this, we get 5,000 multiplied by 2. A little bit. 2 d1y minus d2y plus theta 1 plus theta 2 1/5 plus minus 3 d1y minus d2y minus 2 theta 1 plus theta 2 1/4 plus theta 1 times 1/3 plus d1y. All right. So the next step here is going to be to distribute. Okay. So we're now we're going to be tackling all those scary parentheses terms. Well, let me pause here because I know probably people are still writing down. So are there any questions on anything we've done so far? Okay. All right, so let's go ahead and distribute. We have 5,000. All right, and so we distributed 1/5 through here, so we're going to have a 2/5 d1y minus 2/5 d2y plus 1/5 theta 1 plus 1/5 theta 2. Okay, and we have a minus 3/4 d1y plus 3/4 d2y minus 1/2 theta 1 minus 1/4 theta 2, okay, plus 1/3 theta 1 plus 1/2 d1y. We're almost done, I promise. Okay. All right, so after you distributed here, we have a lot of kind of pieces to pick up. And so what we're going to do is we're going to combine all the like terms together. Okay. So basically, we're going to combine together all the d1y terms, all the d2y terms, all the theta 1 terms, all the theta 2 terms. Okay. All right, so let's look at the d1y terms first. And so we have a 2/5 here, we have a minus 3/4 here, and a 1/2 here. Okay. All right, and so if we combine those together, we have 2/5 minus 3/4 plus 1/2 is d1y. Okay. Next, we have all the d2y terms. So we have minus 2/5, we have positive 3/4. We have minus 2/5 plus 3/4 times d2y. Okay. All right. Next, we have all the theta 1 terms. So we have a 1/5 here. You have minus 1/2 here and a 1/3 there. Okay. Am I missing one? Oh no, that's 3. Yeah. So you have 1/5 minus 1/2 plus 1/3 theta 1. Okay. And then finally, we have the theta 2 term. So we've got positive 1/5 and a minus 1/4 there. Okay. And so we have 1/5 minus 1/4 theta 2. Okay. So from here, our next step is just going to be to simplify. So we're adding a lot of fractions together. And so let's just add them all together into 1. So we have 5,000. It's going to be multiplied by 3 over 20 d1y plus 7 over 20 d2y plus 1 over 30 theta 1 and then minus 1 over 20 theta 2. Okay. So let's go ahead and multiply 5,000. So finally, the 5,000 gets to do something. It's kind of been sitting and waiting in the wings for a long time, but now it finally gets to go in. Okay. And so if we multiply everything by 5,000, we get 750 d1y plus 1750 d2y plus 500 over 3 theta 1 minus 250 theta 2. Okay. All right. So it's been quite a journey. So we've been integrating and doing algebra for the past 20 minutes, but we're just about there. Okay. Because remember, all of this that we've been evaluating on the left-hand side has just been the left-hand side of that equation. Remember, on the right-hand side of this equation, we had f1y d1y plus f2y d2y plus m1 theta 1 plus m2 theta 2. Okay. So this right here, this is the other side of the equation. And so I wrote this kind of very intentionally because, you know, if you kind of line these up based on the terms that have the same nodal deformations, you'll see that we have expressions here for all those nodal modes. Okay? And so what this is basically saying is that F1y is equal to 750 newtons. Okay? F2y is equal to 1750 newtons. Okay? M1 is equal to 500 over 3 Newton meters, and M2 is equal to minus 250 Newton meters. So these are the nodal modes, okay? And so if you want to do this problem with the direct stiffness method and you had that distributed loading, instead of applying that distributed loading, you would apply these nodal modes instead, okay? So what we're saying, let me go ahead and recap the whole thing. So this is where we started. That's where we started. But after doing these computations, what we're saying is that an equivalent way to do this is to say, we have a single load here of 750 newtons. So that'd be F1y. Okay. We have a larger load on this side, F2y, of 1750 newtons. Okay. And then the moments that we apply, we have a moment of 500 over 3. So we have M1 is equal to 500 over 3 Newton meters. Okay. And then we have a moment M2. M2 here is going to be a minus 250 Newton meters. Okay. Yeah. It is in the opposite direction. But, and so it would be, but if I drew in the opposite direction, that I would have to make it a positive 250. And so I drew the arrow going counterclockwise, and then the negative will swap it back. Yeah, so the true direction for M2 would be in the opposite direction, in the clockwise direction, but but then the sign would change that. So these distributed loading problems, they are quite time consuming, but the nice thing about this is that most of the time ANSYS is going to handle this for you, and so ANSYS will kind of do this automatic conversion, so you don't have to. But just know that even in ANSYS, this is still happening underneath the hood, because in order to actually apply any kind of loading, you have to know what its value is going to be at the nodes, and so this is kind of a necessary step. Any final questions on this before we wrap it up for the week? Okay, all right, so that's all we got time for. And so, that's going to be it for the direct stiffness. So this is going to be the cutoff for the midterm exam. Okay, and so on Tuesday, we're actually going to get back into ANSYS. And so next week, next week's an activity week. And so Tuesday, we're going to go over how to do unsteady simulation in ANSYS. And then Thursday, we're actually going to implement. So, I know it's quite a few things happening at once, but this is it for the theory. But don't worry, ANSYS Activity 5, I'm not going to have it due until way after Thanksgiving break. And so, next week is just kind of a good time to have it. But I don't want you to actually work on it until after the midterm exam and after you do your project proposal. Okay, so I know there's like 5 different things happening in the class at once, but I'm trying to stagger the due date so it's not too overwhelming. All right, so thank you guys for coming. So hope you guys enjoy the rest of your weekend. Stay warm. It is quite cold outside. I've had to go pee like 5 times today already because my bladder is shrunk like crazy. So stay warm, and see you guys next week. Hey guys. Zoom people, any final questions before I close it up? Okay, yeah. Oh, that sounds cool. Yeah, definitely. Definitely. Let's talk once you guys have decided on the models, and we can talk about how to simulate that in FEA.
Yeah, Professor, I have a question.
Yep.
I may have heard wrong, but you said you don't do exams in your class, but I believe you said we had a midterm the week of Thanksgiving break, right? Like the week before.
Yeah. So we don't have a final exam, but we do have a midterm exam.
Oh, okay. And then you said we were gonna go over a study guide with that, right?
Yes, yeah. So next week I'm going to write a study guide just so you have it. So basically, to study for the midterm exam is going to be, the problems are going to be very similar to the problem set that's out there right now, and then the study guide will help you with the conceptual information. So if you use those two and you're good on those things, that's probably as good as you can prepare for the exam.
Okay. All right. Perfect. Thank you.
Yep. Mm-hmm. All right, Zoom people, any final questions? Stay warm, it's cold. All right, I'll see you guys next week. Have a good weekend.